Hello, in this video I'd like to talk about semilinear sets. A very important type of set or sequence within automata theory is the eventually periodic set, or the eventually periodic sequence. An eventually periodic sequence is exactly what you might think it would be. It's just an infinite sequence that has some behavior, some random behavior, up to a certain point, and then beyond that point it's just the same chunk repeated infinitely. Think, for instance, the decimal digits of any rational number. Just like I did in the weak S1S video, we can translate back and forth between sets of natural numbers and sequences of characters from some finite alphabet. If we have a sequence of characters from some finite alphabet, we can, for each of the characters, look at the set of indices within the sequence where those characters appear. And vice versa, if we have a subset of the natural numbers, we can turn it into an infinite sequence of characters, 0 or 1, where it's a 0 in indices that aren't in the original set, and a 1 in indices that are in the original set. This gives us the notion of an eventually periodic set. So we say that a set is eventually periodic with a particular period if there is some value of n, some natural number n, such that beyond that point, an element is in the set if and only if that element plus the period is in the set. In other words, beyond a certain point, whether a particular element is in the set or not just depends on its remainder modulo p. And we can pick whichever set of remainders we want, and we can pick whatever behavior we want less than n, but there just has to be some point where it starts becoming periodic. Semilinear sets are a generalization of the eventually periodic sets, so that instead of looking at a subset, so an eventually periodic set is a subset of the natural numbers, but a semilinear set is going to be a set of tuples of natural numbers. So we're in some sense moving into a higher dimension. But before we talk about semilinear sets, I want to talk about some different perspectives on the eventually periodic sets that will help motivate our definition of the semilinear set. So the first fact that will guide us is that if we have a particular first-order logical formula of Presburger arithmetic, the set of values of x, the set of natural numbers that we can plug into the formula to make it true, is going to be an eventually periodic set. And vice versa, if we have an eventually periodic set, it's actually fairly simple to construct a first-order logical formula with one free variable that is true exactly for elements of that set. Another key fact about the eventually periodic sets is their relationship with regular languages. If L is a regular language, the set of lengths of words in L is eventually periodic. And sort of vice versa. If we have a set that is eventually periodic, we can find a regular language whose set of lengths of words is that particular eventually periodic set. And if we only have one character, then this is exact. If we have a regular language on one character, again, the set of lengths is going to be eventually periodic, and vice versa. If we have an eventually periodic set, then the set of words of those lengths is a regular language on one character. Of course, if we have more than one character, we can encode some information in the choices of what characters go where, and that information, it could be uncomputable even. So this isn't like a precise classification of the regular languages. There are certainly non-regular languages, and in fact non-computable languages, whose set of lengths of words is eventually periodic, and in fact whatever really nice set you want. All of the gross part of that set can take place entirely in what sequences of letters show up in that language. While these two facts motivate our particular multidimensional abstraction that'll give us the semilinear sets are more commonly defined in terms of what are called linear sets. So we can view the d tuples of natural numbers kind of like vectors. They don't have the properties of a vector space. Normally we expect the scalars to have multiplicative inverses, and we expect addition to have additive inverses. We expect to be able to subtract. You can't subtract necessarily elements of this space. Sometimes you can subtract, but not always. Nonetheless, we can make sense of expressions treating these like vectors. And so we describe a subset of d tuples of the natural numbers as linear if there's some natural number vector c and some tuples, possibly empty, of natural number vectors p1 through pn, such that the set is the set of all c plus some multiple of p1 plus some multiple of p2 up to some multiple of pn, where the multiples are natural number multiples. So what these subsets look like is they look like they start off at the point c, and c is an arbitrary point in the space of d tuples of natural numbers. So here we're thinking about points on a d-dimensional integer lattice that are entirely non-negative in their coordinates. So if we're thinking about this in one dimension, it's just going to be the non-negative integers. If we are thinking about this in two dimensions, it's just going to be the top left quadrant of integer points. And if we're thinking about this in three dimensions, it's just going to be the non-negative octant of the integer lattice. So let's imagine that we're in two dimensions now. C is some point with integer coordinates in the top left quadrant. And then we have, let's say that we have three different vectors, p1, p2, and p3. So if we have a vector p1, and again, this is going to be a natural number vector, so that when we add it to C, we get another point on this lattice. And we can add some natural number of copies of P1 to get other points within this set. So these points here would all be in the set. Now if we had another, we call these period vectors, P2, we can add some natural number of copies of P2, and we can also add combinations of them. So we can add one copy of P1 and one copy of P2, or two copies of P1 and one copy of P2, and so on and so forth. And this keeps going. In some sense, we've created a transformed version of n squared in this space here. And again, all of these points have natural number coordinates to them. Finally, suppose we have some other period vector, let's say something like this. Then again, we can add an arbitrary number of copies of that new period vector and arbitrary numbers of copies of these other period vectors to just get a whole bunch of points. This is bad drawing, but it kind of looks like a cubical lattice that's been deformed and then flattened down onto the plane. And we can have as many period vectors as we want. We can have just tons of them taking up a whole bunch of space, or we can just have one period vector and have just kind of a one-dimensional subset of this space. Or we can even just have 0 period vectors and just talk about a single point as being a linear set. So these are the linear sets. A set is semilinear if it is the finite union of linear sets. Generalizing our connection with Presburger arithmetic, if we have a first-order logical formula of Presburger arithmetic, then the set of tuples of natural numbers, right, that's going to be a subset of this space here, that satisfy that particular first-order logical formula, when we plug them in, is going to be semilinear, and in fact this is an exact characterization of the semilinear sets. Every semilinear set is the set of all tuples that make a particular first-order logical formula of Presburger arithmetic true. Let me prove the reverse direction first, that if we have a semilinear set, then it's given by a first-order logical formula in Presburger arithmetic. I'll start by showing you how the proof works that every linear set can be describable in the first-order logic of Presburger arithmetic by going through an example. And then, of course, if we want to take the union of sets, that just corresponds to logical OR. So suppose that we have a linear set whose base constant is the vector 1, 2, and whose period vectors are 3, 4, and 5, 6. So this set defined here is simply the set of all pairs x, y, such that there exists a k1 and there exists a k2, where x, the first coordinate, is just the sum of the first coordinates of this term here. So the first coordinate of c plus k1 times the first coordinate of p1. Remember that we can talk about multiplying by specific natural numbers in Presburger arithmetic. 3k1 is just shorthand for k1 plus k1 plus k1. And then 5 times k2, right? The first coordinate of p2 times the constant that we're multiplying p2 by. And y is the second coordinates of this term here. And that's it. This simple description here describes this particular linear set. And again, we can OR formulas like this together to get semilinear sets. What's more, if we take a first-order logical formula of Presburger arithmetic and turn it into the corresponding specification as a finite union of linear sets, and then translate it back using this technique, we can take any first-order logical formula of Presburger arithmetic and turn it into a very nice disjunction of formulas that simply look like this. So formulas that are a disjunction of formulas that look like this are actually a normal form for the first-order logic of Presburger arithmetic. So now I just want to show that if we have a first-order logical formula, then the set of tuples that make it true when we plug them in is semilinear. And similar to the sorts of proofs that we were using when we were talking about weak S1S and Buki arithmetic and the word logic, I'm going to prove this by induction on the construction of phi. But first, just to get some intuition for what's going on, I'd like to take some formulas of Presburger arithmetic that we already know and look at the set of tuples of numbers that satisfy those formulas as sets of points in space. Of course, we can talk about whether or not one number x is greater than some other number y, and that's going to look like this set of points here, where this is 0, 0, this is 1, 0, this is 2, 0, and so on and so forth. This here is a semilinear set with base point 0, 0, and period vectors like this. Every point in this set can be written as 0, 0 plus some natural number multiple of 1, 0 plus some natural number multiple of 1, 1. So the set of points where 2x plus y is divisible by 5 look like this grid here. And again, we're going to have the base vector of 0, 0, and period vectors that look like this. Any point in this set can be written as 0, 0 plus some number of multiples of these 4 vectors here. If we want to talk about the tuples where x plus y equals z, then this is actually, well, it's going to be a set of points in 3 dimensions, and it's just going to form a hyperplane in that space. And it's just going to be 0, 0, 0 plus some number of multiples of 1, 0, 1 plus some other number of multiples of 0, 1, 1. And then finally, if we want to talk about the tuples where A is odd, B is any natural number, and C is 0, then this is just given by the set of all vectors of the form 1, 0, 0 plus k1 times 2, 0, 0. This is going to make the first coordinate 2k1 plus 1, which is going to be any odd number. And then this k2 here times 0, 1, 0 is going to allow us to make the second coordinate be any natural number we want. So even though on the surface semilinear sets might not seem that expressive, a lot of sets that we want to talk about are not just semilinear, they're actually linear. It's only when we start combining them with Boolean operations, or maybe we want to modify whether or not specific points are in or out of the set, to add in some random points to the set or take out some random points from the set, that we actually wind up talking about semilinear sets as opposed to just linear sets. And of course, this property of being able to toss in individual points or take out individual points is something that we really want to be able to do with semilinear sets. Because of course, in the first order logic of Presburger arithmetic, we can add in some Boolean stuff to make specific exceptions for specific points, whether they're in the set or not. And of course, working with sets that are eventually periodic, we can change these sets at any specific point, whether a number is in the set or not, and that won't affect the eventual periodicity. This sort of being closed under finite modification is pretty obvious if we're talking about adding in points. We just union in single point linear sets. Showing that the semilinear sets are closed under removing a point is a little bit trickier, however. Let's prove this for just individual linear sets, and of course if you have a union of linear sets, you just remove the point from each of them, if it's in there at all, and then that removes the point from the entire semilinear set. So suppose that we have a linear set. It's going to be some sort of base point and a bunch of period vectors that kind of form a cone in space. And we have a point in the set that we'd like to remove. What we need to do is take our original linear set and break it up into a linear set that looks like this. It has the same periodic pattern, but we've kind of shifted the base point by some multiple of one of the period vectors, the period vector that defines this side of the cone. And so what that does is it takes the periodic pattern of the whole thing and just shifts it over so that it isn't covering anything in here. And specifically, it doesn't cover the point that we'd like to get rid of. And then we take our set and also shift it along this period vector here to cover this cone. And what that means is that these two linear sets are going to cover this entire space here. They're going to cover all of the points in the original linear set that were in this part of space here. And then we just add in singleton linear sets. Remember that every singleton is a linear set. For all of the points in this space here, there's only finitely many points in here, so there's only going to be finitely many points in our original set that are in this space here. And we just add in all of those linear sets into our union. And that allows us to describe this linear set with a point removed as a semilinear set. Another commonality between semilinear sets and eventually periodic sets is that the periodic pattern that gets repeated can actually be whatever we want. Suppose that we have a semilinear set with base point here and two period vectors. These period vectors define a unit parallelogram to them. And that unit parallelogram is only going to have finitely many points in it. By default, this semilinear set just consists of the points that form the lattice that these period vectors define. However, suppose that we have some sort of configuration of points within this unit parallelogram. then we can define a semilinear set, not a linear set, but a semilinear set that takes this pattern here and duplicates it in all of the copies of the unit parallelogram that wind up being defined by this lattice. And the way that we do this is we simply have each of these be the base point of a separate linear set with period vectors p1 and p2. And so this point is in the set, and then adding as many copies of p1 as we want will take us to the corresponding point in other parallelograms, and adding p2 will take us to the corresponding point in parallelograms up here, and of course we can navigate to whatever copy of this point we want in whatever parallelogram we want. And then we have a separate linear set that's going to have this as a base point, and that's going to access all of these points. And then we have a third linear set whose base point is here. And so we can actually, even if we don't want this point and copies of it to be in our semilinear set, all we need are these points as base points, and we can take whatever pattern we want and replicate it across all of these parallelograms. And so we can produce whatever periodic behavior we want using semilinear sets. So we could, if we wanted to, view the basis of our semilinear sets not as individual linear sets, but rather as groups of linear sets that all have the same period vectors that define a pattern that gets repeated throughout the cone defined by that particular semilinear set. It's enlightening to take a look at what happens when we take several of these periodic semilinear sets and combine them together when they intersect with each other. So let's say that we have some semilinear set that defines a periodic behavior within this cone here, and another semilinear set that defines a periodic behavior within this cone here. We're going to get some sort of periodic behavior here, and some sort of other periodic behavior here. And what's going to wind up happening is we're going to wind up with a bunch of different regions, and each region is going to have its own periodic behavior. And it doesn't matter how many of these basic periodic semilinear sets we combine together, we're still going to get all of space is divided up into a bunch of different regions, and each of those regions has some periodic behavior on it. Of course, it's not really meaningful to say that we have some periodic behavior on some finite piece. The periodicity could be much larger than the piece, and so we could have whatever pattern we want within that finite piece. But when we have these infinite pieces here that are defined by Boolean combinations of these cones, they are going to have some periodic behavior in them as they go off to infinity. And what you can do using some closure under Boolean operations, reasoning, and some other complicated things is prove that every set that has these cone-defined regions and has periodic behavior on each of those regions is going to be a semilinear set. And I claim that this is all of the semilinear sets. That every semilinear set is simply, we divide the world up into cones and pieces that are combinations of cones, and then we have whatever periodic pattern we want in each of those pieces. We now hopefully have enough intuition to prove that every set which is first-order logic describable in Presburger Arithmetic is a semilinear set. Again, the proof is going to be by construction on the formula phi. Step one, just to make our lives a whole lot easier, is to relationalize. Remember that the terms in this language can be quite complicated. They can be linear polynomials. And so an atomic formula in this language is an equality of these linear polynomials. But that's going to require us to reason about linear polynomials when we don't really have to. All we need to do is show that the most basic atomic formulas, things like formulas of the form x plus y is equal to z correspond to semilinear sets, which we just did. Any more complicated formulas can be built up from these atomic formulas by introducing new variables for intermediate expressions. Let's say now that we have some formulas phi and rho that each correspond to semilinear sets, and we want to prove that the set of all points where phi or rho is true forms a semilinear set. Well, an OR just corresponds to taking the union of two sets. And if we think about it, semilinear sets are just finite unions of linear sets. And so just by construction, if we want to union together two semilinear sets, we just union together those two unions of linear sets. So it's by construction obvious that we're closed under OR. Although I am disguising a bit of a technicality that I talked about previously when I was talking about regular logics, in that we could be looking at a formula where phi has only two free variables, x and y, and rho has only two free variables, y and z. So by induction, we know that phi of xy describes a semilinear subset of the xy space, and rho of yz describes a semilinear subset of the yz plane, and somehow we have to combine them together, we have to union them together to describe a semilinear subset of three-dimensional xyz space. In order to do that, we need to be able to take a description of the set of all points xy, where phi of xy, as a semilinear set, and expand it to a description of the set of all points xyz, where phi holds of x and y, and z can be whatever we want. Then we can take the union of this set here with the expanded version of this set here for rho, and that will correspond to the semilinear set that we're trying to describe here. So we need to somehow be able to take a semilinear set in 2 dimensions and build it out into 3 dimensions. Let me show you how this is done constructively for a basic linear set, and then you can fill in the rest of the details. Well, let's say that phi of xy is true exactly for points of the form 1, 2 plus k1 times 3, 4 plus k2 times 5, 6. In order to take this set into 3 dimensions, we just add on a third coordinate. This here will describe the set of all points x, y, z, where x and y belong to this original set, and z is 0. We can then add in a new period vector to allow z to be whatever it wants. And again, if you apply this sort of operation to all of the linear sets within a semilinear set, it will expand it into higher dimensions in the way that we need it to in order to get this step of the proof to work. Next, we need to show that if phi corresponds to a semilinear set, then there exists an x such that phi of x, and maybe there are some other free variables here, also corresponds to a semilinear set. This operation corresponds to a projection flattening down the x dimension, right? We don't care what value of x makes this tuple work. We just care about the values of y and z and other variables where there is some x that makes this tuple work. So we want to take those various x values that we get and just kind of project them away, flatten everything out into just the yz subspace. Next, we need to show that if we have a particular phi corresponding to a semilinear set, then not phi also corresponds to a semilinear set. This corresponds to taking the complement, right? We're trying to show that the complement of a semilinear set is also a semilinear set. And just looking at the definition, this isn't obvious at all. But if we're thinking about semilinear sets as being piecewise periodic over a bunch of different pieces, all we're doing is complementing those periodic behaviors on each of the pieces. I'll link to some other ways of proving that the semilinear sets are closed under complementation in the description. And then finally, if we're talking about things like phi and rho, or for all x phi, we can just take these things here and describe them in terms of these things here, right? Phi and rho is just not phi or not rho. And so we just take this, turn it into this, and then use the inductive steps that we've already done. And for all x, phi of x is equivalent to, there does not exist a counterexample, so we can just take this, turn it into this, and use the inductive steps that we've already proved. Essentially, we're thinking of ands and universal quantifiers as almost a syntactic sugar that doesn't really need to be part of the language, just to make the proofs by induction easier. We can also generalize our word lengths result. Suppose that we have some sort of function called count that takes in a word and outputs a tuple. There's going to be one element of this tuple for every letter of our alphabet. So there's 3 letters of our alphabet here, and it's just going to be the counts of each of the letters. So the first character is A, there's 3 A's. So count of this word is going to be 3. There's 5 B's, 5, and there's 1 C, 1. So this takes in a word and outputs a d-dimensional vector of natural numbers. And the claim is that if we apply the character count function to every word within a particular regular language, we're going to get a semilinear set. And we can sort of go backwards. Every semilinear set is this set here for some language L. But there are also plenty of non-regular languages that also have semilinear word counts. In fact, the interesting thing in the context where you're most likely to encounter semilinear sets is in terms of the context-free languages. The character counts for context-free languages also form semilinear sets. And in fact, there are even some languages that aren't context-free that have semilinear word counts. Somehow you're doing a bunch of interesting things, not with the numbers of different characters that show up in the word, but in the orders that the characters show up in the words. And of course, when we apply the count function to a word, we lose that information, and that information could have been really complicated. So we have a really complicated thing, and it's turning into a nice, simple semilinear set. So semilinear sets have lots of equivalent characterizations, right? We can talk about them as the word counts of regular languages, we can talk about them as the sets describable in Presburger arithmetic, or we can describe them as finite unions of linear sets. And my intuition is that there's lots of other ways of characterizing the semilinear sets as well that aren't obviously equivalent. So thanks for watching. Let me know if you have any questions or comments down below, and I hope to see you in a future video.